Then the gear terminologies are continued. Next one is working depth. It is the radial distance from the addendum circle to the clearance circle. It is equal to the sum of addendum of the two machine gears. Then tooth thickness. It is the width of the tooth measured along the pitch circle. Then tooth space. It is the width of space between two adjacent teeth measured along the pitch circle. Then 18th. Backlash. It is the difference between the tooth space and the tooth thickness as measured along the pitch circle. Theoretically, the backlash should be zero, but in actual practice, some backlash must be allowed to prevent jamming of the teeth due to the tooth error and thermal expansion. Then, face of the tooth. It is the surface of the gear tooth above the pitch surface. Then, flank of the tooth. It is the surface of the gear tooth below the pitch surface. Top plant. It is the surface of the top of the tooth. Face width. It is the width of the gear tooth measured parallel to its axis. Profile. It is the curve formed by face and the flank of the tooth. Then fillet radius. It is the radius that connects the root circle to the profile of the tooth. Then path of contact. It is the path traced by the point of contact of two teeth from the beginning to the end of the engagement. Then length of the path of contact. It is the length of the common normal cutoff by the addendum circles of the wheel and pinion. Arc of contact. It is the path traced by a point on the pitch circle from the beginning to the end of the enlargement, that is engagement of the given pair of teeth. The arc of contact consists of two pairs, that is arc of approach. It is the portion of the path of contact from the beginning of the engagement to the pitch point. Then arc of recess. It is the portion of the path of contact from the pitch point to the end of the engagement of a pair of teeth. The next one, condition for constant velocity ratio of toothed wheels, that is law of gearing. Let Tt be the common tangent and Mn be the common normal to the curves at the point of contact Q. From the centers O1 and O2, draw O1M and O2N perpendicular to Mn. A little consideration will show that the point Q moves in the direction Q1C1 when considered as a point on wheel 1, and in the direction Q1D then considered as a point on wheel 2. Let V1 and V2 be the velocities of the point Q on the wheels 1 and 2 respectively. If the teeth are to remain in contact, then the components of these velocities along the common normal Mn must be equal. So angular velocity omega 1 by omega 2 is equal to O2n by O1m is equal to O2p divided by O1p. So this is the law of gearing. Then it's defined as the term law of gearing. The common normal at the point of contact between a pair of teeth must always pass through the pitch point. This is the fundamental condition which must be satisfied while designing the profiles for the teeth of gear wheels. It is also known as law of gearing. A velocity of sliding teeth. The velocity of sliding is the velocity of one tooth relative to its mating tooth along the common tangent at the point of contact. that is V. Velocity suffix S, it specifies sliding of teeth. So W1 plus W2 into Q into P. Then forms of teeth, cycloidal teeth, involute teeth. The difference between involute and cycloidal gear. The cycloidal gear, in cycloidal profile, pressure angle varies from maximum at beginning of the engagement, reduces to 0 at the pitch point and again increases to maximum at the end of engagement, resulting in improper running of gears. While in involute profile, pressure angle remains constant throughout the engagement period. This results in smooth running of gears. Due to complex manufacturing, cycloidal gears are costlier, while involute gears are simple to manufacture and these are cheaper. So this is the profile of involute tooth profile, and that is the next one is the cycloidal tooth profile. So advantages of involute gears. The most important advantages of involute gears is that center distance for a pair of involute gears can be varied within the limits without changing the velocity ratio. This is not true for cycloidal gears, which requires exact center distance to be maintained. In involute gears, the pressure angle from the start of the engagement of tooth to the end of the engagement remain constant. It is necessary for smooth running and less wear of gears. But in cycloidal gears, the pressure angle is maximum at the beginning of engagement, reduces to 0 at pitch point, starts decreasing and again becomes maximum at the end of engagement. This results in less smoothing running of gears. The face and flank of involute teeth are generated by a single curve, whereas in cycloidal gears, double curves, epicycloid and hypocycloid, are required for the face and flank respectively. As the involute teeth are easy to manufacture, when cycloidal teeth in involute system, the basic rank as straight teeth and the same can be cut with simple tools. Advantage of cycloidal gears. Since the cycloidal teeth have wider flanks, therefore cycloidal gears are stronger than involute gears for the same pitch. Due to this reason, cycloidal teeth are preferred especially for cast teeth. In cycloidal gears, the contact takes place between convex flanks and the concave surfaces, whereas in involute gears, the convex surfaces are in contact. The condition results in less wear in cycloidal gear as compared to the involute gears. The difference is wear is negligible. Cycloidal gears, the interference does not occur at all. Though there are advantages of cycloidal gear, but they are outweighed by the greater simplicity and flexibility of the involute gear.